Okay, so picture this. You've got a single point, and it's being yanked in 3 different directions all at the same time. How in the world do you figure out where it's actually going to go, and with how much force? Well, today we're going to crack this classic physics problem, and you'll be surprised how straightforward it can be.
Take a look at this bracket. You might see something like this in a bridge or maybe an engine part. Right now, it's caught in a serious 3-way tug-of-war. Now, at first glance, it just looks chaotic, right? But believe me, there's a really clear, logical method to figure out exactly who wins this fight. And this isn't just some problem from a textbook. This is exactly how engineers make sure our structures can handle all the complex stresses of the real world.
So this is the big question we're trying to answer. We're looking for what's called the resultant force. Think of it as the one single force that could step in and do the exact same job as the other 3 combined. It's the net effect, the final outcome of this entire tug-of-war.
So how do we find it? Well, here's the secret. We need to stop looking at these weird angled forces directly. The real trick, the key to the whole thing, is to break each one of them down into its fundamental building blocks, a simple horizontal pull and a simple vertical pull.
And this is the concept that makes it all possible. Force components. Just imagine any angled force is like a flashlight, and it's casting 2 shadows. One shadow is purely horizontal, falling on the x-axis. The other is purely vertical, on the y-axis. Once we break our 3 messy forces down into these super simple x and y parts, the whole problem suddenly gets way easier to handle.
All right, let's dive in. We'll start with the 1500 Newton force, and we'll keep track of it using the color pink. As you can see, it's pulling up and to the left. Our first mission is to figure out the exact size of its horizontal and vertical shadows, its x and y components.
Okay, now hold on. Before we touch a calculator, we absolutely have to talk about direction. In physics, direction is everything. You got to get it right. So, since this force is pulling to the left, we're going to say its horizontal component is negative. And since it's pulling up, its vertical component is positive. Seriously, getting these plus and minus signs right is where most mistakes happen, so this step is absolutely crucial.
Now we can find the actual numbers. And for that, we just use a little bit of basic trigonometry. For the horizontal part, the x component, well, that's the side adjacent to the 35-degree angle, so we use cosine. And remember, it's going left, so we make it negative. For the vertical part, the y component, that's opposite the angle, so we use sine, and it's going up, so that one stays positive. Simple as that. Excellent. 1 down. 2 to go. Let's move on to our next force, the 80 Newton one. We'll track this one in orange. This guy is pulling up and to the right.
We're just going to run the exact same playbook here. The force is pulling to the right, so its x component is positive. It's also pulling up, so its y component is also positive. And just like before, we use cosine for the adjacent horizontal piece and sine for the opposite vertical piece. See the pattern?
And now for our final contender, the 120 Newton force in blue. Now, I want you to pay really close attention to this one, because there's a common little trick hidden in how they've shown us the angle.
Did you see it? That 30-degree angle? It's being measured from the vertical y-axis. But our simple sine and cosine formulas, they're set up to work best with the angle measured from the horizontal x-axis. But hey, no problem at all. We know there's a 90-degree angle between the axes, so we just do a quick calculation. 90 minus 30 gives us the angle we actually need to use, which is 60 degrees. Now that we have that corrected 60-degree angle, the rest is easy. This force pulls right and up, so both of its components are going to be positive. You know, this is a perfect example of why having a system is so important. It makes you slow down and catch those little details. All right, we've officially finished the deconstruction phase. We've taken all 3 of those tricky angled forces and broken them down into their simple x and y pieces. So now it's time to put everything back together and finally see the big picture. And this table right here, this is where all that hard work pays off. We've got all our components neatly organized. All we have to do now is some really simple addition. We're just going to add up the entire horizontal column to get our total x force, which we call Rx. Then we'll do the same for the vertical column to get our total y force, Ry.
So just look at what we've accomplished. We've taken this entire problem with 3 messy angled forces, and we've boiled it all down to just 2 simple forces, a tiny net pull to the left and a really big net pull straight up. Now all that's left is to combine these 2 to get our final answer.
So how do you combine a horizontal force and a vertical force to find the diagonal force they create? Well, for that, we're going to call on our old friend Pythagoras.
His theorem is the absolute perfect tool for this job.
The formula is beautiful in its simplicity. It just tells us that the magnitude of our final resultant force R is the square root of Rx squared plus Ry squared. So let's go ahead and plug in the numbers we just calculated from our table.
Okay, this is it. We have our totals, we have our formula. After all that work breaking things down and adding them all back up, we are finally ready to reveal the one single force that does the job of all three.
So we just plug in our total Rx, which was negative 1.59, and our total Ry, 241.38. And notice something interesting. When we square that negative number, it becomes positive, which makes perfect sense because right now we're just trying to find the overall strength of the force, not its final direction just yet.
And there it is, our answer, 241.4 newtons. That is the single combined force that's actually acting on this bracket. All that complicated pulling and pushing from 3 different directions boils down to one single pull of this magnitude.
So let's just do a quick recap of the powerful toolkit you've just learned. You can solve basically any problem like this just by following these steps. 1. Break every single angled force into its x and y components. 2. Carefully use plus or minus signs to show direction. 3. Sum up all the x's and all the y's separately. And finally, number 4, use Pythagoras to combine those totals into one final force.
So we figured out the strength of the final pull, 241.4 newtons. But, that's really only half the story. The final question is, what's the precise angle of that force? In which exact direction is it pulling? Well, that's the next piece of the puzzle in vector analysis, and it's a great challenge for you to think about. Thanks for watching.